Okay, we're going to spend a lot of time speaking about various complexity classes in this and next few lectures. So I thought it would be good to kind of give a quick pre-review of what we're going to deal with, kind of give a high-level picture of what's going on. So what do we know so far, right? We know about an undecidable problem and, of course, decidable problems. Now, inside the decidable problems, there are the problems that we can solve. Period. But we care now on the complexity. So, running time complexity. So, the first class to care about is the exponential time class. What is exponential time? It's algorithm that the running time is of the following form, n to the sum of constant, right? So it's e to the power of some polynomial. And as we already discussed, this is pretty awful running time, but it is what it is. It's still an interesting class. Okay, and what do I mean by class, right? So we are dealing with decision problems, right? Because algorithms, to speak about them formally, it's easier to speak about the decision version where you give an instance and you have to answer yes or no about the instance. So a decision problem is an EXP class if there is an algorithm that solves it in exponential time, right? Okay, inside EXP we have a subclass called P-space. P-space is all the algorithm that can be solved using polynomial space. And it's easy to argue that if you have polynomial space, then simulating the algorithm, going to all possible states, and as such the overall running time is bounded by exponential. So that's why it's contained in EXP. Of course, those two classes are pretty awful. So the class we really care about is P, polynomial time, that we had seen. And all would be wonderful and great if all interesting problems were in P, but unfortunately we know that this is not true, right? So in containing P, there are two decision problem classes that are very important. One of them is NP, which is non-polynomial deterministic, which is what we're going to spend today talking about. Those are all the decision problems for which, if the answer is yes, then you can verify the answer. Given a certificate, you can verify the answer quickly. More on that shortly. Then we have the CoNP class. CoNP is you can verify no. Right, so I give you an instance, the answer for this instance is no, then you can verify it in polynomial. One can give you a proof and you can verify it in polynomial time. So those concepts are very weird. Don't worry if you don't currently understand what the hell I'm talking about. Hopefully we will get to the stuff and it will become clearer later on. But the important thing to know is that a lot of natural problems like independent set and clique and so on are in NP. And we don't know if they are in P, right? So as far as we know, it might be that CoNP and NP are in fact P, right? So those two classes are the same and they're contained in P. The belief is what's drawn in the picture, right? The belief is that CoNP and NP are not equal to P. But we don't know, right? This question is open for the last 40 years. Okay, above this, we have problems that are NP-hard. NP-hard problems are problems that if we could solve in polynomial time, then NP and CoNP, NP would be equal to P, right? It would say that everything collapses and all the problems in NP can solve polynomial time. Notice that NP-hard not only contains problems in NP, it also contains problems that are much harder. In fact, it contains even undecidable problems. So it's a kind of a very bizarre class. But the basic importance is that there would be a lot of optimization problems, not the decision problems, but the corresponding optimization problem. That would be in NP-hard, because NP-hard is much more flexible than NP. NP really is just for decision problems. Okay, so this is the picture. This is how we believe the world look like. And then we are going to spend a lot of time looking on this class here. This is the NP-complete problem. NP-complete problems are problems that are believed to be the hardest problems in NP. Those are problems that if you can solve one of them, then you can solve all of them in polynomial time, and in particular, you can solve all the problems in NP in polynomial time. So, and we will see that there are a lot of natural problems that are NP-complete, for which we don't know we have a polynomial time, and we in fact believe that there is no polynomial time, right? So if you show that the problem is NP-complete, you essentially show that it's intractable. You cannot solve it efficiently, and you need to move on in life, which is of course always true. And NP-complete sometimes is written as NPC.